I'm hitting record right now, so you're ready.
Awesome. Okay, thank you. Let me actually figure out what I'm going to say. Okay, right. So thanks so much, all of you, for coming back. Let me see if I can share my screen. So yesterday we covered, in a slightly scattergun and fast-paced and not particularly rigorous way, some connection between ideas in abstract rewriting theory and multi-way systems, and possible formalistic connections to aspects of quantum mechanics. And what I want to try to do today is to convince you that these sort of slightly hand-wavy suggestions I made about relationships between completion procedures and orthogonal projections, and relationships between collections of rewrite rules and unitary evolution operators, those kinds of things, I want to try to make those sort of correspondences a bit more precise, and hopefully try to convince you that there is a sort of a nice geometrical intuition for what the multi-way evolution graph and what the branchial graphs actually are, and that sort of corresponds really rather nicely with the sort of with the geometrical intuitions that one has in the geometrization of quantum mechanics, and that at least in certain cases where essentially in cases where the multi-way system obeys a strict sort of what's called a modularity property, which is kind of a weakened version of a distributivity property, that in fact we can prove that the combinatorial structure of the multi-way evolution graph limits to the subspace structure of a projective Hilbert space, as one would study in ordinary quantum mechanics. So I want to kind of walk you through that derivation today. But before I do that, I'm just going to quickly finish off saying something that I was going to say yesterday, but I didn't really feel like it, which was, you remember when we did the derivation of SR and GR, we started with this very, very kind of naive toy case where we considered the embedding of the causal network into some lattice, which we said, you could define a naive multi-way, a naive Minkowski norm on. And we use that to derive, at least in the kind of 1+1 dimensional case with a grid-like causal network, we use that to derive certain features of the Lorentz transform. I think as a kind of intuition builder, it's useful to do the same thing here. So if we now consider taking the multi-way evolution graph and embedding it in a lattice in exactly the same way, but now where the coordinates are those of time, as in the causal network case, but now rather than being a spatial coordinate system x, we instead have a branchial coordinate system y, which is sort of the natural coordinatization not on the spatial hypergraph, but on the individual branchial graphs. And then we can define a norm that's much like the naive Minkowski norm we defined before, which I'm going to provisionally call the multi-way norm, which again allows us to separate, which allows us to classify states in the multi-way system as being time-like states if the norm is negative, branch-like states if the norm is positive, and entanglement-like, which I'm going to use. I'm going to use that terminology in a slightly suggestive way as the analog of the light-like separation or light-like states or light-like events that you'd see in an ordinary space-time causal network. The essential intuition behind that being, as we'll see in a little bit, that sort of that whereas in ordinary space-time one defines the conformal structure in terms of light cones, here we define the conformal structure of our multi-way evolution graph in terms of entanglement cones that effectively state which microstates of the universe have had time to get entangled with which other microstates. And so then the boundary of that cone is the thing that defines the entanglement-like separations in the multi-way evolution graph. But as I say, we'll make that correspondence a bit more formal in a minute. So then, given a pair of states, you can then sort them out into whether they're time-like separated, branch-like separated, or entanglement-like separated, just like we did in the space-time case, based on the value of the multi-way norm of the difference between their two coordinates. So essentially, what that's allowing us to say is that if we see AA and ABAB, then we know that these are time-like separated states. ABA and AAB here would be branch-like separated states, and sort of AA and AAB would be entanglement-wise separated states. And so this is obviously a very simple kind of Minkowski-like, grid-like multi-way evolution graph for some very simple string substitution system. And I'm showing it in its kind of default foliation, which you can think of as being like the multi-way analog of the cosmological rest frame that we considered in the space-time case. And okay, I have a little note here, but as I say, I'll explain this correspondence in a bit more detail later. But the reason why we're able to say that it makes sense to say, that if a pair of states are entanglement-wise separated, the reason it makes sense to say that they are entangled in some sense is that even though they may not share a causal edge in actual space-time, they may not appear to be causally related in space-time, but they can still share causal edges with respect to the multi-way causal network. So they can be connected with branch-like separated causal edges, even if they aren't separated with space-like separated causal edges. Sorry, even if they aren't connected with space-like separated causal edges. And so in effect, what you end up with is the situation where two microstates, even if they're not spatially local, they can still be correlated by virtue of the fact that they have some common ancestry in the multiway evolution graph. And so and then as we mentioned yesterday, it's the branchial graphs that characterize the ancestry distance between the microstates that exist in the multiway evolution graph. So essentially, this is why we've been saying sort of so far that in effect it's the branchial graphs that designate the patterns of entanglements between elementary eigenstates. Okay, so then for this particular foliation of the multiway evolution graph, this is the sequence of branchial graphs that one would see. This is the particular sequence of eigenstates that one would see as being in linear superposition. And so then if we considered instead an observer corresponding to a different foliation, they would see a different time-ordered sequence of superpositions between those eigenstates. And therefore, if they attempted to perform a measurement, their completion procedure would be different. They would be attempting to impose equivalences between a different collection of microstates. And so the observation of the eigenstate that gets collapsed, that their measurement collapses the system down to, would be different. The eigenstates as seen for observers performing different measurement operations with respect to different foliations will in general be different. So we can see that explicitly if we instead consider taking this sort of rest frame foliation and boosting it like some kind of Lorentz boost, but instead of being some physical, instead of corresponding to something concrete like physical motion in space, this is something much more abstract. This is sort of related to motion in branchial space, which corresponds to some parameterized change of observer. It's some parameterized change in the sequence of measurement operations that the person observing the system is choosing to do, and so they're seeing a different sequence of linear superpositions, and hence they're performing when they actually come to perform a completion procedure, that they will end up seeing different results. So in this case, this is the branchial graph this is the sequence of branchial graphs as seen by this observer in the boosted frame. So whereas before we saw that all of the branchial graphs were connected, in this boosted frame, the branchial graphs are disconnected. They have disconnected components. So what that's indicating is with respect to this observer's in this observer's attempt to make sense of what they see in the multiway evolution graph, they see states as being unentangled, which the previous observer in the rest frame would have seen as being entangled. Okay, so then in exactly the same way as we defined a conformal structure for sort of the Lorentzian manifold in the case of a causal network, we can define an entanglement structure on the multiway evolution graph, an entanglement structure on branchial space. So we can introduce concepts like evolutionary precedence, which is the analog of chronological precedence in space-time, and we can introduce concepts like entanglement-wise precedence, which would be the analog of causal precedence in space-time. And then, so then given a particular microstate in the multiway evolution graph, we can examine its evolutionary future, its evolutionary past, and also its entanglement-wise future and its entanglement-wise past, which just as in the space-time case, correspond to the strict interior of a light cone and the interior plus boundary of a light cone, respectively. Except in this case, of course, it's not a light cone; it's an entanglement cone. It's an illustration of which quantum states have had an opportunity to become entangled, and which states were sufficiently far away in branchial space that they cannot yet be entangled, and we'll come on to it in the next section that I kind of want to walk you through. I'm going to explain exactly why we think there's a sort of maximum rate of entanglement, why entanglements propagate in branchial space at some finite speed, and why that connects with things we actually know of in sort of ordinary experimental quantum mechanics. Okay, so this is, so entanglement future, entanglement past, evolutionary future, and evolutionary past. These are the corresponding ideas of causal future, causal past, chronological future, and chronological past, respectively. We don't just have to define them for individual states. We can define them actually for surfaces, for collections of such states. And so then the branch-like hypersurface, this allows us to intuit the branch-like hypersurfaces are like the space-like hypersurfaces. They're like the Cauchy surfaces that we defined with respect to the causal network. And so then the property that the multiway evolution graph can be foliated in this way, that it doesn't have closed time-like curves and it doesn't have kind of degenerate evolutionary connections between branch-like separated states, which is the analog of global hyperbolicity in the space-time case, is essentially saying that it is possible to set up a well-posed Cauchy problem in the context of one of these multiway evolution graphs if we take a continuum limit. And that ability to set up a well-posed Cauchy problem is what allows us to say that we can define an invariant measure, and that in turn is related to the unitarity of evolution. And we'll see that in just a little bit. Okay, so then much like in the causal network, then the foliation of the multi-way evolution graph can be parameterized by a local gauge choice in branch yield space, except this time we're not specifying it in terms of a lapse and a shift, we're specifying it in terms of a lapse and a branch yield shift. But in all other respects, the combinatorics is the same, so the specification of the foliation is the same. And so then the branch-like hypersurfaces are the level sets of the universal time function that we set up in the process of constructing this, in the process of constructing a function t that sort of maps states in the multi-way evolution graph onto integers corresponding to their branch-like hypersurface. So then we can think of an observer. Before I had the slightly hand-wavy definition of an observer as being, some macroscopic object in the multi-way evolution graph who perceives a definite evolution history. Now we can actually give a much more precise definition. They are a time-ordered sequence of equivalence classes between microstates, and that time-ordered sequence is parameterized by this universal time function. Okay, so you remember in deriving special relativity and general relativity and making connections to Lorentz symmetry and local Lorentz symmetry, we introduced this notion of causal invariance, which allowed us to guarantee that independent of the choice of foliation, the combinatorial structure was always the same. And we related this to the concept of global confluence. There's an analogous sort of property that we can consider here, a property that we call multiway invariance, which is the statement that the combinatorial structure of the multiway evolution graph is invariant under the choice of foliation. That's something that's a bit less well developed with respect to mathematical logic. It's related to the property of completability in term rewriting systems. So you can have a term rewriting system that is not globally confluent, but is nevertheless completable in the sense that you could perform a kind of appendix completion procedure, obtain a globally confluent rewrite system which has the same deductive closure. And so that's a weaker condition than global confluence, but it's still, it's still a stronger condition than nothing. And that's, effectively multiway invariance is the analog of that. We're not saying that the system is causal invariant, but we're saying that it's possible to set up a foliation of the multiway evolution graph into these branch-like hypersurfaces, which the observer could then complete in such a way as to obtain a causal invariant evolution history. Okay, so we saw before sort of analogs of what you might call inertial reference frames, inertial quantum observation frames. But just like in the space-time case, there's nothing to prevent you from having the analog of gravitational field configurations. You can construct effectively arbitrarily wild foliations of the multiway evolution graph. And so this is arguably more like what an actual quantum observation frame would look like in the non-inertial case. Okay, but there's more to life than just the multiway evolution graph. You also have to consider not just the individual states, but the causal relations between the events that separate those states. So all of the structures that we've considered so far, from the space-time causal network to the multiway evolution graph, can really be considered to be kind of coarse-grained or fine-grained approximations to this much more fundamental object, which is the multiway causal graph. So the multiway causal graph is the structure that contains information not just about the multiway evolution, but also about causal connections. So if we construct a multiway evolution causal graph here, where all of the blue nodes correspond to the global states, yellow nodes correspond to the events, orange edges correspond to the causal relations, gray edges correspond to the evolution edges, then what we're saying is we can take this evolution causal graph and we can essentially factorize it into a multiway evolution graph on the left, shown on the left here, and a total multiway causal graph, which we show on the right. And actually, in the same way as it's possible to reconstruct the spatial hypergraph from the information in the causal network, it's also possible always to reconstruct the multiway evolution graph from the multiway causal graph. So multiway causal graphs are a slightly sort of complicated object because they contain the causal relations not just from space-time, not just on single evolution branches, but between different evolution branches. And so even though this is a relatively simple example, this is more like what they appear to sort of look like in practice. But nevertheless, it's still possible to perform these factorizations, even if the multiway evolution graph is sort of arbitrarily complex. But here's the point. In the two types of fundamental types of networks that we've kind of constructed coordinatizations of so far, the causal network and the multiway evolution graph, there are only two types of separations that one has to consider. In the causal network, there's time-like separation and space-like separation. And in the multiway evolution graph, there's time-like separation and branch-like separation. But the point is that the multiway causal graph has all three types. There's time-like, space-like, and branch-like separations, and they're all distinct. They all have to, whatever norm you define on that space has to effectively distinguish between those three. So just like in space-time, when we have to, what one has to consider the time-like and space-like separations as having different signs with respect to the standard space-time metric, we have to do the same thing here. So, the hand-wavy way of saying this would be, we need to have 3 independent numerical directions in order to make an effective distinction between the space-like separations, time-like separations, and branch-like separations. Now, of course, we already used positive integers or positive numbers for the space-like separations and negative numbers for the time-like separations. So without loss of generality, we can use imaginary numbers for the branch-like separations. And so then the natural metric that's induced on the multiway causal network is one in which values are complex rather than real. And I'm going to give a more rigorous sort of explanation of why we can do that, and why it's actually necessary to do that now. It's related to this thing called Sylvester's law of inertia for quadratic forms. And so what it is essentially saying is that the number of one has to have a distinct sign of eigenvalue in the metric tensor for every distinct type of subspace every distinct type of subspace that exists within your space. So every subspace that you want to keep distinct has to correspond to a quadratic form with an eigenvalue that has an independent sign from the other eigenvalues. And so this is why in the space-time case, if you want to be able to separate time-like and space-like separations, you need to have 2 signs, and it's why now in the quantum situation we need to have at least 3 signs. It's actually okay. This particular statement is just for real quadratic forms. There's an extension for quadratic forms defined over arbitrary over arbitrary complex Hilbert spaces and things like that. Okay, so one immediate issue though is that we now have we have an overdetermined system, if you like, because in the space-time case, when we just introduce positive and negative numbers, that's sufficient to separate space-like and time-like distances, and it kind of gives you no more than you need. But if we also introduce complex numbers, then even if we use positive imaginary numbers for the branch-like separations, we also have negative imaginary numbers, which now have no direct correspondence with respect to this space. So in other words, because we're trying to keep an odd number of linear subspaces distinct, there is one additional degree of freedom that we've introduced, a redundant degree of freedom that's been introduced by introducing a metric tensor that has 4 independent signs of eigenvalues. So in order to be able to get rid of that redundant degree of freedom, what we're saying is that we have to define an equivalence class between a large collection of states in the multiway evolution graph. And so that's that's the reason, loosely speaking, that's the reason why we obtain a projective Hilbert space as opposed to a regular Hilbert space. The projectivity, the invariance of the structure of the metric under projective transformations is exactly the thing that allows us to get rid of the additional redundant degree of freedom that was introduced by switching to a complex norm. Okay, so this is not particularly interesting. This is kind of just bookkeeping. If we now go to if we consider an embedding in this 3-dimensional thing that this object which has 3 independent components, this multiway Minkowski lattice, then we can define a norm with respect to that. The natural norm is complexified. And so now we have notions of time-like, light-like, entanglement-like, space-like, and branch-like separations, which you might immediately see are not necessarily mutually exclusive. In particular, space-like separations are sort of a special case of branch-like separations, and light-like separations are a special case of entanglement-like separations, and so on. And that, as we'll see in a second, actually has implications for things like the wave-particle duality. So what that's really saying is, if space-like separation is just a special case of branch-like separation, then what you're saying is that your different foliations of the multiway causal network will see different pairs of states as being either space-like separated or branch-like separated. That will be something that is observer dependent. So to put that another way, if you see a collection of geodesics propagating in the multiway causal network, how do you interpret that collection of geodesics? We've discussed in the relativistic case that we can think of a bundle of geodesics propagating in a causal network as being like the trajectories of a collection of test particles that we use to determine the curvature of the space. And we also discussed how a bundle of geodesics propagating in the multiway evolution graph is something like a wave packet in quantum mechanics, because it's, if each state is an eigenstate, and so a collection of eigenstates that lie on a branch-like hypersurface corresponds to a linear superposition, then the propagation of a geodesic bundle is the propagation of a linear is the time evolution of a linear superposition of those eigenstates. It's effectively a wave packet or a polarization ellipsoid, if you want to be a bit more sort of mathematically fancy. So the statement that the multi-way Minkowski norm doesn't allow you to globally separate space-like and branch-like separation, that there isn't mutual exclusivity here, corresponds to the statement that for observers in certain reference frames, for observers with certain foliations of the multi-way causal network, a bundle of geodesics can either appear to be purely space-like separated or purely branch-like separated, or a collection of both. And if they appear purely space-like separated, they will appear to be a trajectory of test particles, of some cloud of test particles. If they're purely branch-like separated, they will appear to be the trajectory of a wave packet. And if they're a mixture of the two, they'll seem to be somewhere in between. So effectively, the nature of wave particle duality, the fact that different quantum observation frames will perceive geodesic bundles as being particle-like or wave-like, follows just sort of immediately from the fact that there is not from the fact that there is a lack of mutual exclusivity in the separation of states in the multi-way with respect to this naive multi-way Minkowski norm. But just like we did in relativity, I now want to kind of take you through how you can go about deriving something that's a bit more realistic, that doesn't require this sort of ill-defined procedure of doing a layered digraph embedding into this lattice. So that's really what I want to cover today. Okay, but to do that, what we need to do is define a sort of limiting geometry. And that was relatively easy to do in the case of the causal network. We can kind of see how that limits to something that has the same conformal structure as a Lorentzian manifold. But for these branchial graphs, which appear to be sort of exponential, so the nice thing about the causal network is that in the cases we're interested in, it does limit to something that's sort of finite dimensional. With these branchial graphs in general, they seem to grow exponentially. So in other words, they don't seem to limit to anything that has a nice kind of fixed finite dimension, which is immediately a problem, because it means that the same techniques that we applied in the causal network case, we actually have to adapt to deal with this kind of exponential dimensional case of the branchial graph, because of course at each layer of the hang on, wait, can you guys see this? Can you guys see my lecture slides, or am I sharing the wrong thing?
We can see them.
So you can see this thing called the limit of branchial space.
Yeah, we can see it.
Okay, cool. Sorry, Zoom was just complaining. I had some yellow box appearing that I wasn't sharing the right thing. But okay, that's fair enough. Thanks. Okay, so we're going to have to adopt. We have to adapt the techniques somehow in order to make this analysis work. All right, but even in these cases, we can see that we're getting something that does appear to have a limiting geometry. So, we were considering before branchial graphs for just elementary string substitution systems. In the hypergraph cases, you get branchial graphs that have more realistic geometries. And so one immediate question we can ask is, what is the sort of natural metric we define on a space like this, if it does indeed correspond to a well-posed geometrical space in the limiting case? Well, in the purely discrete case, even before we take a continuum limit, we can define a notion of a metric, because we know what it means for two states to be separated by a certain distance in the branchial graph. What it means is, if they're separated by a distance of n, if they're separated by n branchial edges, what it means is that the ancestry distance between those microstates is n with respect to the multi-way evolution graph. So in other words, you would have to go back up n levels in the multi-way evolution graph before you found a common ancestor. If two states are totally disconnected in the branchial graph, that's an indication they have no common ancestry. So we can formalize that in terms of algorithmic information theory. So some of you may have encountered this concept of Kolmogorov complexity, the idea of quantifying the complexity of an object in terms of the length of the shortest program, the number of bits contained in the shortest program that would be required to generate that object. You can generalize that notion to obtain this concept of a Levenshtein distance or an edit distance. And the kind of the most complete generalization is this thing called an information distance, where the idea is, if you have two arbitrary states, two arbitrary objects, you can ask what is their information distance? What is their distance with respect to algorithmic information theory? And then the idea is it's a measure of the distance in terms of what is the length of the shortest program? What is the Kolmogorov complexity of that would be required for you to transform one of those objects into the other object? So you fix some universal Turing machine, you fix some universal programming language, and then you ask, if we take if those two objects are input states for that universal Turing machine, what is the minimum of the what is the minimum length of the program that would be required either to reduce x to y or to reduce y to x? And well, in some form, the natural metric that's defined on one of these branchial graphs is an information distance, right? Because if you think of the multi-way evolution graph as performing a computation, as we discussed yesterday, then what we're asking is, what is the length of the shortest program? What is the length of the shortest rewrite sequence that allows you to derive...
Jonathan.
Yes, yeah.
Jonathan. Hey. I think your slides...
Hello? Sorry.
What
Hello?
should we be seeing?
You should be seeing something related to information distance.
We see NA multi-way Minkowski.
Yeah. Okay. Yeah. Right. That's what I was checking. Okay. So this is wrong. Let me. Okay, that's what I was talking about. Can you see this now?
Yes.
Yes. Yeah.
Okay. Perfect.
Information
Sorry
distance in branchial space. Now the okay, got it.
Yes. Yeah. Okay. Sorry about that. Yeah. Okay. Zoom's complaint at me was correct. Okay. Yes. So that may have seemed a little bit obscure. So let me quickly recap that. So I was what I was trying to show you was this kind of thing here, which appears to have a nice limiting geometry. And asking, you know, what is the obvious choice of metric for that for a space like that? And so the point I was making was that in the discrete case, the natural metric is this thing called the information metric or the information distance. Because what you're really asking is, what is the minimum length of the rewrite sequence you would need to apply to derive states X and Y from some common ancestor state? So the ancestry distance in the multi-way evolution graph is really a form of an information distance metric. That was the main point I was trying to make. And so you can think about this as being a little bit like an edit distance on strings or an edit distance on hypergraphs, but it's really it's a way of quantifying in terms of algorithmic information theory the concept of an ancestry distance in something like a multi-way system. So like I say, it's a natural extension of the concept of Kolmogorov complexity. So if we introduce this notation K sort of x bar y to mean the Kolmogorov complexity of if you have a program that accepts input y, what is the Kolmogorov complexity of the program that accepts input y and results in object x? We can denote that by saying k x bar y, in which case we can express the identity, the information distance metric directly in terms of that Kolmogorov, in terms of a maximum of the Kolmogorov distances or the Kolmogorov complexity measures. And it's not too difficult to prove that the information distance metric does indeed satisfy the axioms of a metric space, except that the metric inequalities have some term that's on the order of the logarithm of the maximum Kolmogorov complexity, and that's essentially essentially what you're doing is you're introducing some additive constant that's related to the translation complexity, because there was some arbitrarity in which choice of universal Turing machine you made in defining the information distance. But if you ignore that arbitrarity, everything else you get is essentially a bona fide metric. It satisfies the axioms of a metric space. So at least in the discrete case, we know what the natural metric on branchial space is. So what happens when we go to a continuum? Well, let's try kind of semi-naively to adapt the techniques we developed in the general relativistic case. What we did before, as you remember, is we tried to take a bunch of these concepts from Riemannian geometry and extend them to arbitrary metric measure spaces by essentially taking the concept of a volume measure in a Riemannian manifold and generalizing it to the concept of a probability measure in some metric space. So we're going to do the same thing. And so some of you will know that we introduced before this notion of a Wasserstein distance, a transportation distance, which is a kind of measure theoretic way of quantifying distances between probability measures. But there's an alternative way of quantifying the same idea, which is what's called an information distance. And the canonical one there is what's called the Fisher metric. And so there's a really interesting kind of collection of interplays between Fisher information distance and Wasserstein transportation distance. There are some situations in which the Fisher metric or the Fisher-Rao metric for certain kind of statistical manifolds is directly proportional to the Wasserstein distance, and that gives you some the situations in which they can be considered equivalent up to some multiplicative constant. Other situations where that statistical manifold has some nice homogeneity property, but the point is that there are two independent ways of quantifying distances with respect to a statistical manifold. In other words, with respect to a manifold in which every point is treated as some probability measure. So whereas the Wasserstein, the intuition for the Wasserstein metric is that it's some transportation distance where you're disassembling measures in one place and transporting those measures to another place, and you're measuring the amount of work done in doing that transportation. The Fisher information metric is more like a it's more like the algorithmic complexity measure. I mean, it's related to this concept of information geometry called the Kullback-Leibler divergence, which is precisely a way of measuring discrepancy between probability measures with respect to some common probability space. And it has nice smoothness properties that in fact aren't satisfied in general by things like the Wasserstein metric. Okay, so although it's conventional to write the Fisher metric tensor in this sort of integral form, we can also write it purely in a matrix form. That's nice because it allows us to make explicitly the correspondence between the continuum Fisher information metric and the discrete information metric that we defined earlier. Because if we rewrite if we rewrite the integral form as an explicit matrix form, then we see it's a metric that's defined with respect to the second derivative of an entropy, of a self-information contribution that is exactly the entropy that one would see in ordinary information theory. It's exactly the Shannon entropy. And so, as I mentioned here, the implication of that is that as long as your probability distributions are all computable, then the expectation value of the Kolmogorov complexity is exactly the Shannon entropy. And so we can make this nice correspondence between this continuous concept, which is the Fisher distance, and this otherwise discrete concept, which is the Kolmogorov complexity and the resultant information distance. So this gives us a sort of a way of saying that if there exists a continuum limit of these branch field graphs, then the natural distance metric that was the information distance in the discrete case will become the Fisher distance in the continuous case. Okay, so again, as a quick intuition pump, we can think, this is an example of a geometry that's clearly higher dimensional. It's clearly not something we can easily represent in 3 dimensions, that exists, that's constructed by evolving a multi-way evolution system for an elementary string substitution rule. So what we're saying is if we perform essentially a surface reconstruction of this as some higher dimensional object, we're saying that the individual discrete information distances that are represented by the edges will become something like a continuous Fisher information distance. Okay, there's a great, and I just want to show this because they're kind of cool to look at. There's a great diversity of kind of limiting geometries, even in the most elementary cases. So these are the pure, string substitution one-dimensional cases, and in fact, these are even the simplest possible string substitution rules that just have single elements on the left. And even with this extremely restricted class of rules, you still see great diversity of limiting high dimensional geometries. But nevertheless, in every case, because we have, because we know the underlying discrete metric, we also know the kind of continuum approximation to that metric as these branch field graphs get arbitrarily large. That's the second typo I've spotted in this. I need to do a better job of typing these out. Anyway, okay, what does any of this have to do with quantum mechanics? Well, here's the exciting thing. We've already mentioned that actually the space we're considering, which is the space produced by the limits of the multi-way causal network, is one that doesn't have a real norm but actually has a complex norm. And so one question you might ask is if we have some complex projective space, which is what we've essentially defined, what is the natural metric that exists on that space? Well, it turns out the most general natural Kähler metric, in other words, the most natural metric that has compatible complex structure, Riemannian structure, and symplectic structure is this thing called the Fubini Studi metric. It's the kind of canonical metric that you would define on a projective space with a complex norm. And it's the thing that allows projective Hilbert spaces to have non-trivial curvature. So with an ordinary Hilbert space, of course, the Hilbert norm is sufficiently boring that you can't have any non-trivial geometry in an ordinary Hilbert space. An ordinary Hilbert space doesn't have any notion of curvature sort of associated to it. But if you allow for a projective Hilbert space, you can, because you can define a generalized Riemannian metric, a Kähler metric, which is the Fubini Studi metric. And so the general form looks something like this. Okay, so it's, hang on. Zoom is doing something weird for me. Okay, hopefully that's still visible. I keep getting flashing warning messages. I'm wondering what they mean. Okay, so this is the explicit form of the Fubini Studi metric written in terms of some Hermitian form for the underlying complex projective Hilbert space. If we wanted to write it, okay, if we can write it out even more explicitly in terms of index notation, we get something like this. And this is immediately compatible. We know that this is immediately compatible with the Fisher information distance, because in fact, if you take the real part of the Fubini Studi metric, it's equivalent up to, I think, a factor of 4. It's equivalent precisely to the Fisher information metric for this complex projective Hilbert space. And the reason why that's exciting is because the Fubini study metric is exactly something that appears in the geometry, in the sort of standard geometrization of quantum mechanics. If you want to consider states not with respect to an ordinary Hilbert space, but with respect to a complex projective Hilbert space, then the Fubini study metric is the thing, is the thing you use there. And in fact, it's what allows you to sort of explain a lot of concepts like quantum entanglement and Berry phase in terms of essentially oddities in the metric distance sort of endowed by the Fubini study metric. So in sort of things like quantum information theory, you might consider the Fubini study metric over something like CP1, which would be the block sphere. In our case, we're considering the Fubini study metric over CPn for a kind of arbitrarily large value of n, because we know that these branchial graphs limit to sort of arbitrarily high dimensional objects. So if we rewrite the Fubini study metric not in terms of this sort of skew Hermitian form, but just explicitly in terms of the bracket notation, then we can see it's equivalent to this thing called the Burroughs metric, or the Burroughs angle, which is one method of sort of quantifying the distance between quantum states in some Hilbert space. So it's kind of an alternative to things like the trace distance or the fidelity distance. And the Burroughs angle you can think of as being a quantification of entanglement distance. Okay, so that's immediately quite exciting. If we've been able to start from this purely discrete structure, which is the information distance on the branchial graph, and we've obtained something that, at least in the case where the branchial graph limits to a complex projective Hilbert space, we have an object that we know in the by analogy to ordinary sort of geometric quantum mechanics is a quantification of entanglement between microstates. And so this allows us to give a sort of slightly more formal justification to our previous statement that entanglement is essentially a measure of ancestry in the multi-way evolution graph, and that therefore the branchial graphs are really representing patterns of entanglements between those microstates. And we should note here that this notion of projective symmetry, this idea that we can perform projective rescalings of the branchial graph without changing the structure of the norm, that as I say, is a symmetry we've had to impose by the fact that our metric is overdetermined. This is analogous to the statement that the causal structure of a Lorentzian manifold is invariant under conformal rescaling. Except here, instead of saying that we have some network that's invariant under the action of a conformal group, we were actually saying that the resultant network is invariant under the action of a projective group. Okay, so if we stop considering the toy case of the branchial graphs for pure multi-way evolution, and we instead consider the more serious case of multi-way causal networks and their limiting geometries, we get things that are even more complicated, but still nevertheless do appear to have kind of well-posed sort of potentially infinite dimensional geometries in the continuum limit. And so these are the things we're claiming are limiting to projective Hilbert spaces. And as I say, as long as they limit to a space on which we can define something like a Hermitian form over CPN, then we know that this justifies all of the previous claims about relationships between sort of branchial distance and entanglement distance. Okay, so one question you could ask is there any kind of precedence to this notion of having a purely combinatorial representation of a projective space? It seems like a slightly weird idea. I mean, combinatorial representations of spaces like the Lorentzian manifolds, you might be able to get your head around because you can kind of just think of them as being, skeletonizations that you would construct in causal set theory or something. But, with something like a projective Hilbert space or an infinite dimensional projective Hilbert space, is there any precedence for thinking about that combinatorially? Turns out there are a whole bunch. One of them is this concept of a Steiner system that we investigated for a little while before essentially discarding them as being largely irrelevant to this project, but they're a cool structure, so I'll just talk about them for a second. So if you want to construct a finite projective plane, a Steiner system gives you a purely combinatorial way of doing that. So it's a collection of blocks of a certain size and a collection of points that are contained within those blocks. And so you can represent a Steiner system as some graph. And okay, right. Okay, so then if you consider something like the Fano plane, which is the kind of, I think it's the simplest, which is the simplest finite model of a projective plane. It's the particular case where you have 7 points, 7 lines, 3 points in every line, 3 lines through every point, and so I think it's commonly denoted as PG22. So it's the projective geometry on 2,2, and it can be represented by a Steiner triple system. So a triple system where K is 3 and equal to T plus 1. And so this is a combinatorial way of representing the kind of the incidence geometry of the finite projective plane, at least in the simplest case. Okay, so one thing we considered is, can we think of these branchial graphs as being like sinus systems? Can we think of them as being like combinatorial reconstructions of the projective plane? It turns out that's probably not the case, because if you look at the growth rates in something like a sinus system, and you look at the standard growth rates that appear in branchial graphs, they're quite radically different. If you look, so here's the growth rate in these sinus systems simulated by a sequence of hypergraphs. Here are the growth rates as seen in an ordinary branchial graph, and they have radically different structures. Now, the reason why they have radically different structures, we think, is because something like a sinus system as a representation of the finite projective plane is what's called incidence geometry. So in other words, where every line, every edge is actually, corresponds to a line in the projective plane. Every vertex corresponds to a point. And so the sinus system is representing the incidences between lines and points in the projective plane. But there's an alternative notion, an alternative way to construct combinatorial representations of projective spaces, which is, instead of being incidence geometric, is what's commonly called continuous geometric. So continuous geometry is a field of study that was developed, I think, by Birkhoff and von Neumann quite a long time ago, back in, I suspect, the 1930s. Where instead of representing the relative incidences of things like lines and points, you're instead representing the relative containments of linear subspaces. So the idea is, if you consider something like a Hilbert space, what von Neumann and Birkhoff realized was that you can relax the standard axioms for a complex Hilbert space by just describing it in terms of what is the containment structure of the linear subspaces. So you can construct a partial order that is essentially saying, for a given linear subspace, which other linear subspaces is it contained within, and which linear subspaces are contained within it. And given that partial order, you can construct a Hasse diagram for it, like we do in causal networks, and you end up with essentially a directed acyclic graph that is representing the order theoretic structure of that particular Hilbert space. And the nice thing about about sort of containment geometry or continuous geometry is that, unlike incidence geometry, it generalizes not from ordinary Hilbert spaces to projective Hilbert spaces in a very natural way. Whereas something like incidence geometry can really only deal with things like finite projective planes. Okay, so if we take something like a lattice, so in other words, if we take a post set where every pair has a unique supremum and a unique infimum, then we can define a relaxation of the distributivity condition, which we'll call modularity. And then modularity modularity is a property that can be exhibited by a particular pair of elements in that post set, and then the overall lattice can be called modular if every pair of elements in that post set is itself modular. So here's an example of a modular lattice. Essentially, the intuition for what's going on with respect to modular lattices in terms of what we've already encountered in multi-way evolution graphs is that a modular pair, a pair of elements that satisfies the modularity condition, is a one-step resolvent branch pair in the multi-way evolution graph. So we can tell that this particular lattice is a modular lattice because we can see for every place where there's a bifurcation in the Hasse diagram for that post set, there is immediate one-step reconvergence. And so the way that this is stated in terms of ordinary sort of order theory and lattice theory is that this is a post set for which the diamond isomorphism theorem holds. So if we take this lattice, we can think of a generalization of the standard second isomorphism theorem from universal algebra, because essentially we're allowed to do that because the modular lattice can be considered a variety with respect to some universal algebra. It's the algebraic structure that satisfies a particular set of relations in a universal algebra. And so then the second isomorphism theorem becomes the statement of the diamond isomorphism theorem, which is essentially the statement that the modular pairs that all of the modular pairs are reconvergent. Okay, here's a slightly more formal way of saying that. So here's a more explicit example. So here you can see this is a case where we know, because if the common ancestor is the meet of the two elements A and B, and the common resolvent is the join, then we're effectively saying anytime there is a common ancestor within a single step, there is also a common resolvent within a single step. That's what the statement of modularity is giving you. And then the diamond isomorphism theorem gives you a sufficient condition and a necessary condition for the violation of that modularity, which is, which in our case would correspond to the situation where you have a branch pair that does not resolve in a single step. So here's an example of that occurring here with respect to this poset. Okay, so therefore we know that if the underlying multi-way evolution graph limits to something that becomes a modular lattice, then we know that's a sufficient condition for guaranteeing causal invariance, because of it, if one-step branch pair convergence is a sufficient condition for global confluence, and therefore for causal invariance. Okay, so then continuous geometry, this alternative axiomatization of sort of projective Hilbert space geometry that von Neumann developed, considers modular lattices that are complete, continuous, and complementary. And so in other words, all subsets, not only does every pair of elements possess a join and meet, but all subsets of the lattices possess a join and meet, because effectively if you have not just a pair of linear subspaces, but an arbitrary collection of linear subspaces, they should also have a common subspace that contains them and a common subspace that they contain. Complementarity states that effectively you can negate with the exception of the minimal and maximal lattice elements, it's possible to negate any lattice element by taking its complement. That's the notion that for any linear subspace you can take its complementary space. Then there's the continuity property that essentially says the join and meet operations are associative, which is of course trivially true in the case of projective Hilbert spaces. If A contains B and B contains C, then we know A contains C, so we have transitivity. But in particular, we also have that if the overall space in which A contains B itself contains C, that's equivalent to saying that the subspace A contains the overall space in which subspaces B and C contain each other. And irreducibility, which is the statement that there are only two elements that possess unique complements, which are the minimal element and the maximal element in the lattice, respectively. So as long as you have a modular lattice that satisfies all four of those conditions, you can treat that as being the skeletonized version of some projective Hilbert space. So in other words, what that's doing is telling us that our idea that if we have a multi-way evolution graph that is capable of achieving one-step causal invariance, for instance, by a completion procedure, that the axioms of continuous geometry are the thing that justify us treating the multi-way evolution graph as being the poset that represents the containment structure of some projective Hilbert space. Okay, so if all of that is true, what does that tell us about actual quantum mechanics? I'm aware I don't have a huge amount of time left, and I'm also I'm kind of running out of steam in my own energy levels. But okay, we can make it through to the end, I'm sure. So. What does that actually entail? So in the same way as the structure of the causal network placed constraint, the limiting geometry of the causal network placed constraints on what was going to happen in terms of the propagation of geodesic bundles in the causal network. In exactly the same way, the limiting geometry of the multi-way evolution graph is going to place certain constraints on the evolutions of wave packets, on the evolutions of polarization ellipsoids through the multi-way system. And so then, our hypothesis would be that instead of the Einstein-Hilbert action, we're going to get something like a path integral. And so how would something like that work? Well, if you consider the individual wave packets as being transformations from a coset of pure states, which are like the Goldstone modes, which are essentially those are the deformations of the wave packet, but you can also consider rotations of the wave packet, which are transformations from the isotropy group, the pure state isotropy group, which correspond to the Higgs modes. Then that gives us a geometrization. It gives us a way of considering the motion of that particular bundle of geodesics. So then, if each individual pure state is a ray in the projective Hilbert space, which we now believe to be true, right? That corresponds to a single infinite geodesic that is through the multi-way evolution graph. That is the evolution of that particular pure state. Well, now we can make a natural coordinate choice by defining a chart atlas, a coordinate atlas on the CP on the space CPn-1. And so then that allows us to write out the Fubini-Strudi metric in a very explicit form. And then if we want to incorporate, so obviously in the ordinary path integral action, the only contribution is the contribution that appears as a consequence of the magnitude of the individual quantum amplitudes. Sorry, that appears as a consequence of the phase of the individual quantum amplitudes, and the magnitudes are essentially ignored. In the multi-way evolution graph, where the phase is essentially the angle at which the geodesic is propagating, and the magnitude is the path weight of that particular geodesic, is the path weight of the microstates that are obtained on that geodesic. We don't immediately have that luxury, so we have to make an explicit separation between the two. So we have to impose a mild breaking of the projective symmetry, which generalizes the Fubini study metric a little bit. And we obtain this thing here for some radius r that is that is effectively the density sphere. So if we think of each ray, each pure state in this projective Hilbert space as being stereographically projected from some analog of the from some Riemann sphere, then the radius of that Riemann sphere is the thing that's appearing as the coefficient in the generalized variant of the Fubini study metric. So with that coordinate chart defined, what the conjecture that we therefore make is that just like the Einstein curvature tensor, which is the left-hand side of the Einstein field equations, is the thing that's placing constraints on the propagation of the geodesic bundles in the causal network, we would make the hypothesis that this GIK quantity here on the left-hand side of this sort of generalized version of the Einstein equations is what's placing constraints on the propagation of geodesic bundles in the multi-wave causal network. In other words, it's what's placing constraints on the deformations and rotations of the polarization ellipsoid as it moves through this projective Hilbert space. Okay. But in defining a connection, which is what we did, by defining this coordinate atlas, we have implicitly defined a gauge potential. And we don't really know exactly what that means. We don't know what concepts like local gauge invariants correspond to with respect to these Wolfram model systems. We have a conjecture, but we're hoping that, well, maybe Graham might be able to answer this by the completion of his project. But so the current intuition that we're pursuing with respect to what something like an intrinsic gauge potential would actually mean is a set of restrictions on possible orientations of applications of rewrite rules. So if you're considering how you parameterize possible updating orders, we've already discussed how you essentially have to consider the maximally consistent set of space-like separated updating events. So then if you consider the actual hypergraph as being like a fiber bundle, and so where each vertex is like a fiber, then each hypergraph, which is each hyperedge, which is defining a possible orientation of an elementary rewrite rule, can be thought of as like a local choice of coordinate system. Why do I say that? Well, it's because depending on which orientation of the rewrite rule we apply, that will place certain constraints. It will place conditions on which orientations of rewrite rules we can apply in other parts of the hypergraph. So it's as though by making that initial coordinatization choice, there is essentially a set of constraints that are propagating out in some gauge field that are constraining how we can apply that rewrite rule in other places around the network. So here's a simple example of that. These are, this is a simple square network, and we can see there are two possible places in which we could apply this simple replacement operation here. But depending on which of these two orientations we choose, this will place certain constraints on which other orientations of rules we can apply at future steps when we attempt to evolve other parts of the hypergraph. So like I say, the interpretation of that is that the hypergraph is treated as some base space, each vertex is treated as a fiber, each hyperedge is some local choice of coordinate basis, and then essentially causal invariance becomes a sufficient condition for local gauge invariance, because causal invariance it immediately implies that, independent of which rewrite order you choose, the hypergraphs you end up with are either isomorphic or are hypergraphs which have the same underlying causal structure. And so here, if you have causal invariance, that means that it doesn't matter what initial choice of coordinate basis you make. It doesn't matter what constraints propagate out in the gauge field. The hypergraphs you end up with still have the same causal structure. So causal invariance allows us to deduce a sort of a discretized version of local gauge invariance, at least assuming that this particular interpretation of what it means to define a gauge potential is actually true. Okay, so I mentioned that in performing this construction, we have made a separation between the notion of the angle of the geodesic, which is the phase that appears in the path integral formula, and the notion of the weighting, the path weighting, which is the concept that appears in terms of magnitudes of quantum amplitudes with respect to measurement procedures. And so this is something that of course we for notational convenience, we represent with a single complex number, but it's worth noting that in the multi-way evolution graph, they are treated as essentially being independent quantities, where, as far as we know, there's no situation we've yet encountered where you essentially have to accommodate both objects within a single system of equations. Essentially, all of the systems all of the connections to ordinary quantum mechanics we've analyzed so far have either been at the level of the path integral, where the phase is the only thing that matters, or at the level of measurement, where the magnitude is the only thing that matters. And I mean, if people know of any kind of situations where both magnitude and phase, where it's important to consider both magnitude and phase in a quantum amplitude as being on the same level, I'd be really interested to hear about that, because that's that's a place where potentially we might be able to make different experimental predictions from the experimental predictions made by ordinary quantum mechanics. Okay, but just quickly to wrap up, in terms of making experimental predictions that are consistent with ordinary quantum mechanics, two immediate things that follow from making this correspondence between the space-time causal network and the multi-way causal network, and by implying that essentially quantum mechanics is some generalized version of general relativity occurring with respect to the multi-way causal network and with respect to branchial space. One of those is the analog of the finiteness of the speed of light. So, obviously the fact that the causal network is not fully connected, that it takes a sort of non-trivial number of causal edges to traverse from one point in space to another point in space, is the statement that C is finite. And we have the same thing in the multi-way causal network. The multi-way causal network is maybe much more densely connected than the causal network. So the effective speed of light might be much higher, but it's still nevertheless finite. It limits to a finite value if we take some continuum limit of the branchial geometry. So does there exist an analogous notion in quantum mechanics that can be tested experimentally? Well, actually, yes, there does. People have researched things related to quantum speed limits. I think the earliest example of this is probably the Mandelstam-Tamm bound that was proved back in 1945, that gives effectively a time uncertainty relation that bounds the effective speed of evolution as a consequence of energy dissipation. There's a more formal version of the same idea, which is the Margolis-Leviton theorem. And so the way that works is if you consider the evolution of some initial state kep psi naught to some final state kep psi t, and you ask, I want kep psi naught and kep psi t to be observationally distinguishable, is there some minimum time that's imposed by the canonical commutation relations? Is there some minimum value of t that has to have elapsed before those two states become distinguishable? Well, if you take kep psi naught and you expand it out in the energy eigenbasis, and you consider kep psi t to be a solution to the time-dependent Schrödinger equation for some constant energy, then you can compute the overlap. You can project kep psi naught onto kep psi t and consider its real part. And then by applying an elementary trigonometric inequality, you can obtain an inequality for that real part. And so you can then determine a lower bound on the value of t in order for the overlap of kep psi naught and kep psi t to be non-zero. So as long as the average energy is constant and itself non-negative, then and the initial and final states are mutually orthogonal, then that imposes a minimum bound on the evolution time, which is the Margolis-Leviton bound. And you can see immediately that it's proportional to h bar, which is why before I made this sort of slightly mysterious statement in the previous talk about how the maximum rate of entanglement is directly related to h bar, that the effective rate of information propagation and hence the elementary branchial edge length is related to h bar, and that was the sort of the piece of magic that we introduced in claiming that the elementary separation distance with respect to the canonical commutation relations was IH bar. Now we can see why that's actually true. It's the Margolis-Leviton bound that gives us the maximum rate of entanglement, that gives us the maximum rate the maximum rate at which quantum microstates can become statistically correlated, and it's the structure of the multi-way Minkowski norm. It's the structure of this metric that we've introduced on the projective Hilbert space, in which branch-like separations are treated as imaginary numbers, that gives us the I in front of the IH bar. So this is one immediate consequence of the geometry of the multi-way evolution graph that we know is compatible with known experiments in ordinary quantum mechanics. There's also a more subtle thing, which is in the same way as, successively steepened foliations of the multi-way causal network result in something like relativistic time dilation, as we saw in the case of where we were treating Lorentz transformations. What we'd expect to see is that if you have an observer who exists in some boosted foliation of the multi-way evolution graph, that their perception of time with respect to the quantum evolution between microstates would be slowed down by the same effect, because the geometries are the same. In other words, what we would expect to see is some quantum mechanical analog, some multi-way system analog of relativistic time dilation. So we obviously that's something we directly observe when we consider boosted foliations of the multi-way system. So how can we make a connection between this idea and again things that might be experimentally testable in ordinary quantum mechanics? Well, if we interpret the overlap between kep psi naught and its time-evolved version as being some survival probability, then we can ask, after the system has evolved to that future state, kept psi t, what would happen if we take that time interval, the interval between 0 and t, and considering it to be some unit interval, if we just punctuate it by a sequence of orthogonal projections, of instantaneous projections that we can idealize as being like measurement operations? Well, then, if we just perform if we perform a power series expansion in time of this part of the Schrodinger equation here, then we can rewrite then up to second order, we can write the survival probability like this. In terms of this quantity delta H hat. Again, we're assuming constancy of the energy for the system. So then, as I say, if we punctuate this unit time interval by a sequence of instantaneous projections, what's going to happen? Well, essentially, that corresponds to taking the limit as n goes to infinity of this term here, which is clearly going to converge to 1, because this second order the second order term converges to 0 much faster than the first order term does. And so, in the limit as n goes to infinity, this tells us that the survival probability, the probability of measuring kept psi naught and its time evolved version as being the same, is going to limit to 1. In other words, or to put it another way, the overlap between the initial state and the final state becomes 1, and so the initial state and the final state become the same in the limit as we take an infinite number of instantaneous orthogonal projections. So what this is implying is that the more measurement operations we perform, the slower the unitary evolution. This is this thing called the Turing paradox or the quantum Zeno paradox. And it's not limited. I happen to specify it in terms of instantaneous projections and in terms of sort of instantaneous measurement operations. It's a much more general effect than that. It actually applies in essentially in any interaction with the environment. Any kind of interaction with a stochastic field will result in effectively the limit of the survival probability converging to 1. And so this is, again, a concept that we directly see in ordinary quantum mechanics. This notion that as the observer moves to a boosted foliation, as they attempt to perform more and more measurement operations by sampling a larger and larger region of branchial space, which is the analog of motion in ordinary physical space, our formulation, our purely geometrical formulation of quantum mechanics in terms of geodesics in the multi-way evolution graph would imply that their observation of the time evolution would get slower and slower. And again, that's an effect that we can precisely reproduce in the standard Hilbert space formulation of quantum mechanics. Okay, so I'm aware that I've run out of time. And so there are some other things that we may discuss later on in the week if we have time or something, but that's probably enough to be getting on with for now. I think we're supposed to now shift into the group discussion session, which is not in this particular room. So, I mean, I'm happy to take any quick questions before we run out of time here, but otherwise we can shift to the group discussion. Thanks.
I just have a quick, do you have a reference you recommend for kind of just the continuous version of the geometrization of quantum mechanics?
Yes, okay, yeah, sure. There are a bunch, but the one that I'm particularly fond of, okay, there's an Italian guy called Loeffler who has developed a lot of these ideas of essentially reinterpreting quantum mechanics purely in terms of Fubini study geometry. And so he has this notion, it's a slightly hokey notion, but the mathematics is sound. I'm not so convinced about the physical interpretation of it, which is this thing called super relativity, which is essentially a very directly related concept to what we're trying to do, just formulated in a way that I don't completely agree with, where in the same way as the space-time metric tensor in ordinary Riemannian geometry is what determines the geodesic trajectories in the continuum case. The Fubini study metric tensor is what determines the trajectories in this projective Hilbert case. So Loeffler has done a lot of work on the purely continuous version of that. In terms of, as for references of the discrete case, I'm much less confident that there exist any. I at least certainly haven't been able to find any. But I can send you the preprints and papers of Loeffler if that's helpful.
That'd be great. Thanks.
Yeah, no problem.